Have you ever wondered about the key differences between single-phase system and three-phase system? What is the true definition of a three-phase balanced system? Do you need to have the voltage, the current, as well as the impedance? Is it absolutely necessary to have all the impedances equal on every single phase? Can we have a balanced three-phase system if only the voltage magnitudes are equal? When dealing with a delta and a Y network, do we have to follow certain conventions? Do we have a neutral in a delta network? In this video, I'm going to go over all of these questions in detail and provide you an in-depth answer. I conducted a live training session with my FE Electrical and P-Power students to help them better understand three-phase systems. Whether or not you're preparing for the FE Electrical or the P-Power exam, I'm confident that you're going to find this discussion very insightful. So without further ado, let us dive right into it. The way I like students to think about three-phase systems is nothing more than three single-phase systems. Okay? AC, of course, 60 hertz if you're in North America. Okay? And the voltage can be whatever voltage you are working with. It can be low voltage, medium voltage, high voltage. Now, if you want to further think about these single phase systems, think about individual generators. Okay. In the P-Power program, we actually go through synchronous machines, how they are used as generators, how they're used as motors, and so on. Typically, 99% of the times when you think about a generator, that generator is a synchronous generator. Okay. We go in a lot of detail to discuss why induction machines are typically not used as generators. Okay, so we have 3 times sync generators, each generator basically doing its own thing. Okay, that is at a fundamental granular level how you should think about three-phase systems. Now, there are some conditions that we are going to superimpose on top of each of these three single-phase systems. Condition number 1, that the magnitude of voltage that is being generated by each and every one of these each and every one of these single-phase generators will be identical, the magnitude. Okay, which means that if the peak voltage that is being realized, that is being impressed, that is being generated by generator A is, let's say, 1000 kV with respect to a reference point, with respect to a neutral, then phase B, generator B, is also going to have a sinusoidal that is going to peak at 1000 volt. Similarly, phase C is also going to have a peak voltage of 1000 volt. Is that clear? So we have 3 single phase generators. Each one of these generators is basically producing a maximum voltage of 1000 volt or a 2000 volt or a 3000 volt or a 15 kV, whatever that voltage is. It is identical. That's the first condition, the first constraint. The second constraint that we superimpose on these 3 generators is that they have to maintain a 120-degree phase shift between them. That's it. If phase A at any time is 120, okay, generator A is at 120 degrees, generator B is going to be at 240 degrees, and generator C is going to be at 360 degrees. 360 degrees is 0 degrees. So 0 with reference to 120, phase A is 120, the delta is 120. These two guys, 120 and 240, are 120, and then obviously 240 and 360 are also 120. So notice how any combination, any pair of these 3 generators in angular domain is always 120 degrees apart. Okay, clear? These are the only 2 conditions. And when we have the same frequency, okay, we have the same peak magnitude and 120 degree apart, for all practical purposes, they can be in different locations and can still be part of a 3-phase circuit can still be part of a three-phase system. Make sense? This is what your three-phase system is. This is what your three-phase circuit is in its essence. All right. Now, obviously, there are reasons why we prefer three-phase systems over single-phase systems. And the primary reason is that we are able to actually we are able to transfer more power as compared to three single-phase systems. And we also require less copper. Okay. In terms of the peaks, if you notice this over here, this peak appears and this peak appears and then this peak appears, right? There is reduced vibration because of almost constant torque that is achieved by a three-phase system. It's an advanced concept and in isolation difficult to understand. And we discuss this in more detail when we get to machines in section number 3. But the idea is that the three-phase systems are resulting in reduction of vibration because there's almost a consistent provision or application of voltage. In simple terms, that's how you can think about it. Okay, and power is a big thing. Three-phase machines use less material for the same power ratings. Three-phase machines start more easily. If we have a three-phase machine, because there's a rotation of magnetic force, okay, the magnetic field is rotating. That rotating magnetic field allows the motor to start quickly because it locks in. Again, motor starting is a completely different topic in itself. Okay, there are two major types of three-phase systems that we encounter. We have the Y network, and then we have the Delta network. Okay, and we're going to discuss them in a little bit more detail. As far as the voltages are concerned, at the transmission level, these are the voltages that are very, very common: 115 kV, 69 kV, 500 kV. Even 69 kV is also a pretty common voltage. And then at distribution level, we have 15 kV, 5 kV, sometimes even 480 volts that can be considered distribution. The big thing that you need to understand when it comes to three-phase systems is square root 3 and 30 degrees. I cannot overemphasize the importance of square root 3 and 30 degrees. This is going to make it or break it for you on the exam. Whether you're talking about power systems within the context of FE electrical and computer exam, or you're talking about three-phase systems in the context of P power exam. Now, when it comes to P power exam, three-phase circuits are going to impact pretty much everything on the exam. Okay, whether you're talking about per unit systems, symmetrical components, fault analysis, transmission line models, power system stability, power flow, protection and control, all areas of the exam specification are directly and indirectly impacted by three-phase circuits. Okay. So as I mentioned, there are two broad categories of three-phase circuits, two major types of connections. We have the Y connection and the delta connection. So you can have now four variations. Okay. You can have Y connected source with a delta connected load. That is this. We can have a delta connected source with a Y connected load. So that is going to result in this. Or we can have a Y connected source and a Y connected load, and a delta connected source and a delta connected load. So these are the four major categories. And it is important that we get our hands dirty, both in terms of conceptual understanding for all of these configurations, as well as some good quality practice problems, so that we can actually apply our knowledge of phase voltages, phase currents, line voltages, line currents, square root 3, 30 degrees, delta Y transformation, the load impedances appearing in delta, and then requiring us to actually convert them into a Y, the source appearing in delta, and then requiring us to convert it into Y configuration. One thing I want to tell you is that the best way to solve a three-phase circuit, and if there's one thing that you take away from this session, is this: three-phase analysis is best conducted in a YY configuration. Remember this, which means that your source, if it's given in Y, good for you. You don't need to do anything. If it is not given in Y, if it's in delta, convert it into a Y. Okay? And on the load side, it's the same story. If your load impedance is given in Y, good for you. If it's not given in Y, you have to convert it into a Y from a delta. And fortunately, we actually have some very easy transformations that we can do. But it all starts from your understanding, appreciation, and realization that three-phase circuits must be solved, especially when you're doing them on the exam, pen and paper, with calculator. They should always be solved in a YY configuration. If it's not in a YY configuration, nothing else matters. The first step is to convert it into a YY configuration. Is that clear? Okay. So how do we go about dealing with the Y configuration, the delta configuration? It all starts with, first of all, identifying what's given to you. This is how a Y and a delta looks like. In a Y configuration, you have a neutral that is accessible. I'm going to re-emphasize this. We have a neutral that is accessible. Let me write it out. Accessible. All right. In a delta, surprise, surprise, I do have a neutral. Okay. Can you guys see there's a neutral on the delta? There is a neutral on the delta, but it is not accessible. Okay. This is an imaginary point with respect to which all the phases in terms of the magnitude are going to be constant. That's the purpose of this neutral as well. It serves as a reference. It serves as a common point. Okay. So level 3 understanding of three-phase circuits is recognition of the fact that on the Y network, we have a neutral that is accessible. Level 3 understanding of delta network is that in the delta network, we do have a neutral, but it is not accessible. So if our neutral is accessible on a Y network, what can we do with it? We can bring it out. Okay. I can have 3-wire configuration with a Y where I simply take the phases out. And I can also have a 4-wire configuration where in addition to these phases, I'm also bringing the neutral out. Okay. This will allow me to serve single phase loads, and that is a separate discussion in itself. Unfortunately, when we are dealing with delta, okay, this neutral cannot be accessed directly. There are other configurations in delta, corner grounded delta, for instance, where you intentionally take one of the phase, one of the corners, and ground it. Okay. And that's an advanced concept which I discuss in grounding for the P power exam preparation. But as far as the whole mystery of neutral is concerned, remember that in a Y network, neutral is accessible, and in a delta network, neutral is not accessible. Is that clear? How do we identify Y? Y looks like a star, and delta looks like a triangle. But more technically, when we have a Y network, we have one end of all the, think about these as generators. Okay. These are all generators, 3 single phase generators. We have one of the terminals of the 3 generators connected together. Okay. That's how you can identify Y. And this is an inverted Y like this. Doesn't really matter. when we are looking at our delta network, what we have is a closed loop system end to end. The positive of this guy is connected to the negative of this guy. The positive of this guy is connected to the negative of this guy. The positive of this guy is connected to the negative of this guy. So it's like a closed loop system. Okay. So this is your Y and delta for a three-phase circuit. Some conventions over here that I must point out. When you look at the impedances in Y and delta, is there something that stands out to you? For those of you who are observing it closely, let me do a quick back and forth. So these are the sources, okay? And these are the impedances. Anything stands out for you? What is the key difference? In terms of even nomenclature, in terms of the letters, I've given you a hint, right? I mean, as clear as day. When we look at the nomenclature, the lettering, these are all capital letters. They're not small case. These guys are small case. Now you might be wondering as to Wasim, is this really a big deal? And to be quite honest, strictly speaking, it is. Because it is assumed knowledge. If you are going for the PE exam, one step away from getting your PE license, in my opinion, it is fair for them to test your understanding or depth of understanding, I should say, by making a distinction between these two. This is the line-to-line voltage between phase A and phase B on the source side. This is again a line-to-line voltage, again between phase A and phase B, but on the load side. These are the fine details, things between the lines, okay, that you need to understand, in my opinion, if you want to really pack a nice punch on the exam. Maybe not so much for the FE electrical, but definitely for the PE power. Okay. All right. So capital A, capital B, capital C, A, B, C, they emphasize what? That we are operating on the load side. When we have small letters, small a, small b, small c, this emphasizes that we are operating on the source side. Okay. If we have a balanced load, it simply means that all the impedances on each and every one of these phases are equal. Okay. And if we have a balanced three-phase system, it basically means that the magnitude of voltage, the magnitude of current are equal on each of the three phases on the load side as well as the source side. I'm going to repeat this again. A balanced three-phase system means that the magnitude of the voltage and the magnitude of the current on all three phases on the source and the load side are equal. On top of that, so that's one condition. On top of that, each of the phases are 120 degrees apart. Now, if you ask me, Wasim, the voltage magnitudes are equal, but for some weird reason, the current magnitudes are not equal. Then what? It's not balanced. What if the current magnitudes are equal, but one of the voltages is off, not balanced. Okay, the magnitudes are equal for both voltage and current, but 120-degree phase shift does not exist. Again, not balanced. Is that clear? You only need one of these conditions to be violated for the system to be classified as an unbalanced system. Is that clear? Now let's take one example over here. Very quick example. And let's just focus our attention on this. So let's say I have 120 volt source over here with a 0-degree phase angle. And then I have another 120 volt, 120-degree source between phase B and neutral. Good? All right. So as far as the source side is concerned, you can see, and you can basically have another source over here, 120 degree, 120 volt, and minus 120 degree. Okay. All right. So as far as the source side is concerned, you can see that we are maintaining the voltage magnitudes. The phase angles are all looking very pretty, 120 degrees apart. But here's the thing. Z1 is equal to 0.5 ohms. Z2 is 1 ohms. And Z3 is 2 ohms. Okay. If you apply a simple Ohm's law, this current is going to be equal to what? 240, which is basically 120 divided by the impedance. Phase angle is not going to be impacted because it's a resistor. And again, this is a separate discussion altogether. Amps. This current is going to be equal to 120 and 120 amps. And this current is going to be 60 minus 120 amps. If you limit your evaluation of balanced three-phase circuits just to the sources, you might be tempted into thinking that this is a balanced system. But because the impedances are mismatched, they will result in unbalanced in terms of current. Because you can see this is 240, this is 120, this is 60. Is it making sense? This is level 3 understanding that you must have for three-phase circuits, three-phase systems. And the same can be said for the delta network. Okay, so balanced load requires all three impedances to be equal, both in terms of delta and Y. Now, earlier on, I mentioned that the best way to approach a three-phase power system analysis, three-phase circuit analysis, is by using YY configuration, correct? Now, let's say on the exam, you have a delta connected load. All right. What are you going to do about it? The very first thing that you should do is to convert that delta connected load into a Y connection. And how can you do that? It's very simple and straightforward. Simply take each and every one of those delta connected loads, and this is assuming that they're balanced, by the way. In the P Power Reference Handbook, we also entertain the situation, maybe it is on the next slide, when the system is unbalanced. Okay, when ZA is not equal to ZB is not equal to ZC, even then we have a formula that is going to allow us to calculate for each of the phases the equivalent Y impedance. But let's keep things simple. Assume that they are actually equal, and by simply taking one of the three phases as a sample from the delta, we can convert it very easily into a ZY phase impedance by simply dividing it by 3. Now, what does it look like in reality? What it means is that I am now taking my Y, okay, the y that I have figured out, zy, and placing it like this, zy, zy, zy. And the key thing to understand over here is that as far as the line values are concerned, if I do this transformation properly, the line values will not get impacted. And that is the key. Because what happens within this box, if the transformation is done properly using this formula, right now we're looking at the load side. The same thing happens on the source side. But in terms of source, the delta-y transformation is obviously related to voltages. So the key point over here is that if I'm doing this transformation properly, then the line quantities are not impacted at all. Okay? And that's why I can go about transforming a delta load into a Y load for ease of calculation, analysis, and manipulation. Okay, and same is true for the Y on the source side. I hope you found this discussion helpful. If you're preparing for the FE Electrical or the PE Power exam, I would recommend you to check out my website studyforfe.com. It's a one-stop shop that is going to help you streamline your exam preparation. I have an on-demand program which contains lectures and quizzes, mini exams, full-length computer simulated practice exams that will basically handhold you through all the exam topics in a stepwise manner. Thanks again for your time, and I look forward to seeing you in the next video.